Yes, this video is going to be about Simatic S7-1500, basic on the Siemens PLC. There's going to be a little about a norm, IEC norm, which is called 61131, which is about PLCs and how they should look and be programmed. We're going to concentrate on programming mostly. There is a document here describing this briefly. So this kind of basic on PLCs and PLC programming. There's an introduction, and this session is going to go through until programming model 3.4. So what I'm going to do is I'm just going to scroll through this and more or less talk about some issues in here, and mostly the figures that's in this document. So here's a little general on PLCs, what they are. So what a PLC is used for is everywhere in industry. It's used to control processes. It's also used to tool machines, whatever. It's everywhere, and it's versatile, can do everything and nothing. So here for Simatic, the latest PLC range is this range, and we are going to concentrate on this one. Yes, and how they can be programmed and so on. So if you look at these PLCs, there's a variety of PLCs. There are let's say a compact PLC. I don't have a picture of a compact PLC in here, but that's a PLC with a CPU. The CPU is here. The central processing unit is the IQ, the one that's processing the program. And then a PLC has to communicate with the process. It has to manipulate the process, start and stop motors, open and close valves, whatnot, to make something happen in the process. And then the PLC needs to check that what these commands or what it's doing to the process is actually happening. And for that, it uses I/O modules. These compact PLCs, they are compact PLCs containing a CPU and combined with I/O modules. The I/O modules is where the information goes out to the process and you receive the feedback. And then there are modular PLCs shown in this figure. There is a power supply, a CPU, intelligence in the system, and then I/O modules. And these are communication processors where you use serial communication to talk to other devices in your system or somewhere else. So these are Siemens PLCs, and here it says a little about this norm, the IEC norm that's governing how the PLC should work, and this -3 is about programming. Here's a picture of what we call a soft PLC, which is actually a PC with standard let's say PC CPUs. This one hosts the CPU in this CX2042, I think, is an Intel i7 CPU with multi-core cores, and it's running Windows operating system standard. This is from Beckhoff. So there's also a norm from PLC Open that describes how a PLC should work and how it should be programmed. And what's important here is to program the hardware you buy. You need to know how it works. But the programming, the part 3 here, which is the important part, because that's what we have to do. At least we have to program our PLC, the hardware we are buying. The PLC Open, I think there's a link down here to PLC Open, and if you click on that link, you're going to end up here. And here are the guidelines. You need to be a member to get a lot of information out of this, but you can look at this page. So this document up here, what's written here, is out of this page. So when it comes to programming, we have got data types that we are programming on. PLCs, they are binary machine a lot. Programmable logic controller, true, false. They are Boolean. Yeah. Data type. But modern PLCs, they are computers. They are capable computers, so they can work on floating point, which are real complex data types. So they can do quite a bit of this. Yeah, those data types, and then we have got variables. We have got inputs to the PLC, which is a variable. We have got output from the PLC, which is a variable, and we have got neither the internal variables that you use to save information and retrieve information within your program, but also these variables are not accessed directly. The norm specifies something called function and function blocks. A function block is roughly equivalent to a class in high-level language programming. There are functions and function blocks that use these variables, these input and outputs and private variables and so on. If we look at this figure here, what our PLC is, what they call this is, let's say, a configuration, which is everything. They contains a resource, which is a PLC, and a PLC contains a task, and a task is an interface to the operating system. A task can be something, a small program where you can put your program into this task, and this task is executing cyclically on a time interrupt, for instance, every minute, every second, on an external event, let's say a digital input. That's something that's true, false, that come into your PLC, changes from false to true, and then you can execute a task. So a resource, and this program that's made in here. A program is a collection of function blocks and also functions. So this program is called from a task. So the program here is making this program, making the function blocks and the functions that you need to implement your control task, and call it in a task. And a control task is what you want to do, and a task here is a small program that's linked to the operating system in the CPU. Here in ISC, they are called what they call programs, function blocks, and functions. They call it program organization unit. Here in Simatic that we are going to work on, they don't have programs. A program is just a collection of function and function blocks, and doesn't have any inputs and outputs. You can put anything into it or get anything out of the program. Of course you can, but that's through function and function blocks. For a program, as TI Portland Sim doesn't have one, usually you use a function without arguments, without inputs and outputs, no return value. It's going to work as a program. Now when we look at programming languages, we're going to program the PLC. That's what's important. So it's specified more than one programming language, several. But they are textual languages where you write text to do programming, and they have one that's called instruction list. It's assembly, looks something like this. If you want to add or multiply two numbers, load the first number, multiply with the second number, and store it somewhere. And in Siemens, they use something called reverse Polish notation, so they don't follow this norm. So it would first you load the variables, and then you perform the operation, and then you store it. So it load, transfer, instead of store. Load, it's L, and OK, well, the S is lacking here. This assembly programming is not easy to use, and they have a high-level language available for programming, and that's called structured text. It's a structured command language. It's called in Simatic SCL, and the same instruction that you have up here is written on a line. Colon equals is assignment, so y is assigned the product of x1 and x2. It's easy. It's pretty powerful language too. So those are the textual, and then you have got graphical programming languages, two of them, called ladder diagram and FBD. And let's say here is an example of a ladder diagram, which basically is power flow through wires and stuff like that. And here is a contact. There's power here and a zero here, and this is a coil of a relay, for instance. So if there's power on this one, this Y is going to come through and do something in the process. So if we look here at the ladder, if this one is closed and this one is closed, there is power flowing through here down to the coil. Something's going to happen. And if X0 or 1 is not closed, but this one is closed, there's power flowing down here. So this is what we call an OR gate. Either one of these, X1 or X2, no, X3 true, then there's going to be power flow down to this junction here. But X2 has to be true for power to be flow through here. True is then closed and open. So this is called a normally open contact. If it was normally closed, there would be a line through here. So that's an example. This one translated to what they call FBD, which is the other graphical language, is with logic gates. First is an OR gate and an AND gate, and then this is the output. So if we look at, we can maybe look at these two. Here is an OR gate. This is OR, because either one of these is going to make the power flow. Either one of these is going to make power available here. And if there's no power available here, this is an AND gate, and both have to be true for something to come out of the gate. So this is the traditional, these two methods of programming a PLC, or it's a little big. Those are the legacy ways of programming PLC. Nowadays we're writing 2022. As of now, we use high-level language to program PLCs. You can do this a lot more elegant and more convenient than using combinatory logic to program a PLC. And it says a little why not. And there's another one too that's called sequential function chart, which is used for what we call sequences. Do something, wait, do something more, wait, do something more, which we call a sequence. So it could be something, start a motor, wait, open a valve, wait, start another motor, wait, close another valve, and so on. So there's a special way of programming this. Then there's called sequential function chart, which is pretty old. So this is, if you go back here, this is American technology, this is German technology, and this is French technology. So they all got a little bit of what they do in this mode. And then there's another program language which is not specified here, which is called continuous function chart. This is it's highly advanced, but here you have your components. These are function blocks that's just inserted into this continuous function chart, and then you just drag and drop lines between them. That's the way you do programming or configuring your control task, which is a nice way of doing it. Not all PLCs support this. There are the one we looked at, the soft PLC Beckhoff back up there. They have it, and Siemens also newer versions, as of version 17 of the portal. They have this. So now that was the norm. So that governed the PLC and suppliers of PLCs, they should follow this norm, and they do to a certain degree. They are pretty good at following the norm. Now, when the norm was first out, of course, it took some time for the suppliers to just adjust to the norm. But okay, the PLC S7-1500 programmer is an example. Here's a picture. It consists of a power supply. You need power. There's the CPU with network interface for communication, and there's a back plane in the back here, so the CPU can communicate with the power supply, and these I/O modules. I/O is input and output, and you have a digital input, which is true false. That could be, for instance, a light switch. It's either on or off. And we had digital outputs. That could be something that was on and off. Your light is on and off, and we can use a relay to control the light on and off. And then we've got analog inputs and analog outputs. Analog inputs, those are measurements. For instance, temperature from 0 to 100 degrees. Analog outputs, yeah, that could be something like the speed of an electric motor that goes to a frequency converter. Speed from 0 to max RPM. Whatever the max RPM is, we don't know, but it would be something. And the power in this system, in PLC world, is 24 volts DC. The CPU is supplied with that, the I/O modules are supplied with that, equipment in the field is supplied with 24 volts DC. Yeah, that's a quick one. If you look more closely on the CPU, that's this part here. That's a little expanded. I talked about the network interface down here. There are what we call Ethernet here, or a local area net with TCP/IP protocol on it. And here is a legacy connection that's called Profibus. And here's the power supply, 24 volts DC. And what you have up here, there are some status LEDs that tells you whether the program is executing, there's a fault on the CPU, whatnot. And there's a micro memory card with a load memory. If you don't have this memory card, you can't program a Simatic CPU. Here's where the program is stored, the program you make, but internally the CPU has read-write memory, also known as RAM, random access memory, for faster access. And here's a switch. In mid position it's stopped, which means that the CPU can communicate with the CPU, but it's not executing the program you have written, so it can't control the process. In run mode, it's controlling the process, and then if it's spring loaded, the spring return. So if I hold it down, I can reset the memory, and then you lose your program. So often, maybe you want to do that, but be careful. That's the reason why you hold it down for a certain amount of time, so you don't unintentionally erase your program. Yes, and then it's Ethernet here, X1, X2 interface. Here are 2 ports for this CPU. There are 2 ports, so you can have 2 network connections here, and here's 1 port for that. When we look at the CPU and the memory in the CPU, we have got the TI portal, which we use to program Simatic CPUs. And here is what's on your programming device. They call it on your PC, basically. You store this. Hardware configuration, what your PLC looks like. Which is, if we go back here, does it look like I have this CPU, I have this I/O. There are various types of I/O. So that's what they call a hardware configuration in here, your program that you make. The information of project and so on, symbols and comments and whatnot. What's online is, see, there's quite a bit is copied over here, just to this micro memory card, but then there are more data. And then down on the CPU, of course, this is inserted into the CPU, but it's not a part of the CPU. If you remove it, the CPU wouldn't work. But in the CPU, we have got more memory. That's where you store the variables that were defined in the IEC norm, input and outputs and static things and whatever what you need. You have retentive memory, which basically stores values forever. So even if you lose power and the power returns, the values stored in this memory are kept. And then we have work memory. That's you use most of the time. This is the RAM or read-write memory in here, where your program is stored and you store some data, temporary data and stuff in the work memory. And then there are some additional memory areas. Input image, that's going to be explained later on in a later video. And outputs. That's briefly the information. Let's see if you go back here. The information on the input modules, these two, analog input, digital input, are saved in a special memory on the CPU, sent by the operating system, and your program access this memory. And it's also the same for outputs. You access this memory and the CPU transfer it to the modules. Yeah, and then there's a front cover on the 1500. Not all of the CPU has a front cover, but if they do, you can do something here on the front cover. You can look at the status of the CPU. You can even start and stop the program, and you can configure IP addresses and so on. And you navigate and operate with an enter button here and an escape button, and look at the status. And the status LEDs here up here, it tells you about the status, if it's running, if it's stopped, if it's faulty, and so on. The I/O modules look like this. The I/O module that we looked at has a front connector where you connect your I/O inputs or outputs. There's a lid over here in the front, and in the LED it tells you how to connect the type of input that the module can use. And there's also status up here, a green LED, steady green LED, it's running. If it's flashing, it's not configured properly. So that's an I/O module. Here's the status of the LED. Both flashes, hardly defective, we have a new module. And then on the channel, this was a digital input. If it's a green light, there's power flowing into the input. If it's dark, there's no power flowing into the input. So you can look at, see if you look at the front, these LEDs are located here. Here's one. This is for power, it's green, there's power on it, but there's nothing else connected. So the power supply is okay, it's green. And if a digital input is active here, there's power flowing into it, the LED would be green. It's the same for digital output modules too. So those are the modules, and then we would have to interface to these modules. And then we are looking at the types of, let's say, inputs in this case in your process. Let's say this one could be a light switch. You wouldn't have light switches in your process, but you can look at it like this. So how you interface a digital input is two types. You have active. Your input or device in your process is supplying current or voltage, basically 24 volts to your input through an optocoupler, switches this transistor on and off. So if power flow, transistor switches on and the light would go on, and the PLC could read, okay, this is a logic 1 or a through input. For a passive one, then the PLC supplies the 24 volt. This one closes, power flows back in here, down to 0 volt. Light here, the transistor switches on and off. Closed breaker, on, transistor on. Open breaker, no power flow, transistor off. So this is called an optocoupler, light. There's light making this connection between the a light diode and a phototransistor. And this is the principle for passive and active. And these inputs can be either normal open or normal closed. And normal means that the normal state of the equipment in the process. In your light switch, if the normal state of your light switch is open, it's not activated, it would be like this. You have to activate the switch to get a signal into the to the I/O module and through to the CPU. If it's normal closed, your light switch will be normal closed, and we pushed it, it would open, and then the signal would go away. So this is normal open, normal close contact, and those are terminology that's used for these inputs. The normal closed input is considered to be more secure than the normal open, because if the normal state goes to an abnormal state, things are not okay, that would correspond to a wire breakage, and that's the most common error in our process, is wire breakage. So a wire breakage will say the situation or the state in the process is not normal, do something. Your program should do something. Analog input types, you're just going to scroll down here. There are voltage and current and temperature, and here is an example of a current input. And there are also two types. They are called 4-wire and 2-wire. It would basically be the same for the digital one, but either the sensor has its own power supply down here, or it doesn't. The power is supplied from the PLC. And for a 2-wire, it can only be, let's say, your sensing element or your element in your process needs a power supply, and this is the power supply, 24 0 volts. So it uses 4 milliamps to do its stuff internally, and returns the 4 milliamps, and then till 20 milliamps, because it's analog input, so it can be anything between 4 and 20 milliamps, and through a resistor, and then you get a millivolt out of this, and it goes to an analog to digital converter, converts this to a number, for instance in Simatic world, a word, 2 bytes, which is represent 4 to 20 milliamps. And in the Simatic world it is like that. 4 milliamps would be 0, and in this word, and it's an integer value, 16 bits, maximum is 32,767, but 20 milliamps, which is maximum here, would be 27,648 in a Simatic, the use of that range. It's the same here, but then see, it's a little different connection here. Then in this current, there's a current source there supplying the 4 to 20 milliamps. When it comes to temperature, of course, this sensing element could be a temperature, and we deliver 4 to 20 milliamps. But you have something called resistors, or PT100s they are called too, but they are also PT500 and so on. The PT elements, platina elements, are sensing elements. They alter the resistance depending on temperature. And what you can do is to send a small current through the resistance. As the resistance changes, this voltage would change, and the same principle applies that up here. So we just convert the voltage to a number internal. For Simatic, the I/O modules in Simatic, they also have a microprocessor on here, so they are not what you call raw values. They actually compute the temperature with either 1 or 2 decimals. So the number out of the system, out of the microprocessor, after ADC, temperature was 10 degrees. It would either be 100 or 100 1 decimal, 10.0, 100, or 1000 with 2 decimals, which is 10.00. So it's pre-scaled. Then we have digital outputs, which is basically a voltage here. We have got an optocoupler and a transistor, and then we can actuate something. Or we would have a relay if we need more power. A transistor output, not with an optocoupler, can roughly deliver up to 2 amps. And if you need more, or if you have 230 volts or something like that you need, you will need a relay module, or you could put that relay externally here and use this out just to drive the relay, which means that you move the relay out in the process or outside the I/O module and control. Here are the analog output types. Again, we will prefer the 4020 milliamp because it's pretty robust with respect to noise. Yeah. This is just a principle through actuator, electronic, and so on. Then we have got this, the equipment that we have in the process that are inputs to my PLC. They're called sensors. And the components in the process can do something to the process called actuators. For instance, a valve. You can open a valve and water is flowing or something like that. And the way we can interface a sensor in Simatic is that you can have a CPU in a rack like we looked at in the first figure with an analog input module, 4020 directly. We can have smart sensors which can use a network directly, communicate with serial communication, and Simatic uses Profinet. Or we could have something called remote I/O. Remote I/O is basically you take this analog module, put somewhere else, and use an interface module that communicate with the same Profinet with the CPU. Could do. But the sensor delivers 4020 milliamps. So these are a way to do this. You can do the same with analog outputs, same way. You have a module in the CPU, you have a smart actuator that actually can communicate. It's smart, so it can communicate using Profinet, or you can put it in a remote I/O. Digital input is just the same. It's analogous to this. D module central. Normally a digital input is not a smart sensor, so you interface it using remote I/O or with central in your PLC cabinet. Digital output is the same, normally not smart digital outputs, it's too expensive. Down here in the last is Profinet, which is, see if we go back up here, this one, the Profinet, the serial communication. You're just going to look at the figure, you can read this, but Profinet is a network which connects a lot of devices. Here's a PLC. This could be, for instance, an HMI panel. This is not, it's probably a CNC controller, another PLC. Is the remote I/O we talked about. Also remote I/O. Here we can have drives, a frequency converter, communicating or controlling motors, and so on. And then we have motion control. And what it says is, how fast does communication have to be here? Let's say for this I/O, let's say 100 millisecond or a little faster, but we go to motion control there. You have to go below a millisecond range. So, for instance, up to 250 microsecond. I think that it might even be the newer versions might be faster. And when we talked about real-time communication and isochronous real-time communication and real-time is that it's we look at the time constants in the system. This is going so fast that for the time constants in the system it's in real time. And then we've got isochronous real time. Isochronous means at the same time. And then that is when something has to happen exactly at the same time or at the same time. Okay, here's a little about this communication, the way this communicate. I think there's a link to up here. Let's see. I think I put it. Yeah. If we go to profibus.com. look at. Or let's say we can say allow. That's nice. This is Profinet. It's an organization. The information in here that's collected out of this. Information is collected from this homepage. This is a reference. Yeah. And here are the frames. This is in details. You can look at it, but that's on TCP IP. There are packages of frames that's communicated, and then there are location for what you call isochronous, things that has to happen exactly on a given time, and ordinary traffic and so on. So they share the same frames. Now, this communication here is something called Ethernet. CSMACD is a mechanism that's used, and that's what we call probabilistic. Probabilistic means you're going to get your data through to the one you're sending it to, but you never know when. It's not deterministic. It's not every second you second as. It could be 1.1 second, 0.9 second, but never 1 second. Well, of course, statistically it would be 1 second once in a while. And CSMACD says carrier sense multiple access collision detect. And the way this worked originally is that if I have two communicating on the bus, they could access my communication medium and network simultaneously, and they could collide. So that's the multiple access. But what they did first is they listen and say, is this where I want to move my data? Is it free? Yes. Okay, access it. And that works fine most of the time, especially if you have not a lot of devices on your network. But okay, there are two devices, listen to the bus, is free. Okay, send. Bang. That's multiple access. And the collision detect is that these devices say, okay, I'm transmitting this on my network, and I'm reading back what I'm transmitting. And if I'm reading back what I'm transmitting, okay, I'm the sole one communicating on this medium, because it's a common medium. Now, if you're not reading back what you are transmitting, okay, someone else is destroying your communication here. And that's the collision detect. And when they detect the collision, the device that detect the collision, they just jam the bus. And jam the bus means that they just garble the information on the bus. So those who are sending and listening on the bus, they read just nonsense. That's not what I'm transmitting. And what all the devices do is they stop transmitting, wait a configured time, which is not equal for all devices, and the one with the shortest waiting time, listen to the bus, okay, it's free, I can send. And the one with the longer waiting times, listen to the bus, okay, it's occupied, I can send. Wait till the first one is done, and then they again listen and say, okay, send. But then you could, if there's a lot of participants on the bus, of course you could get a new collision. But that's not deterministic, it's probabilistic. And this is the technology that Profinet uses. So how to make deterministic Ethernet, CSMACD? Okay, we need intelligence in that. First, we need separate wires for transmit and receive, so we don't collide with data. And then we need a switch with buffers. And say, okay, there are two hosts, but if the switch just kind of organizes as, okay, these two are transmitted at the same time based on priority and stuff like that, says, okay, your data is transmitted on the network, your data is buffered. You don't lose it, you just save it, and we are going to transmit it at a later time. Still, it's not deterministic, but at least you don't have collisions, so it's collision free. Yes, so that's one part, and then we get to this real-time functionality and stuff that has to do a little with frames. But what we are going to look at the last here is what we call the isochronous real-time communication for Profinet at the same time. And then this switch, okay, it has the buffers because it has to buffer things, but here, if the host one, the host are called in IP networks, this could be PLCs, of course. PLC 1 wants to transmit data to host 2, which could be remote I/O, not another PLC, and that has to happen every 300 microsecond, deterministic. Then these hosts and the switch would open a channel every 300 microsecond, that's really fast, and have a fast line straight through the switch from host 1 to host 2. And if host 3 wanted to send something, the host 3 data would be buffered. This requires a special component called the ERTech component, which is it's manufactured. It's a special component that handles isochronous feed through and buffering. That's used in the switch, and it of course it would need to be in the hosts too. The same. And what it does is say, okay, we have a clock. It's really synchronized clock, and every 300 microsecond, when my clock says 300 microsecond, I transmit. This one says open the channel, and this one says receive. So it's a fast line straight through. The real-time part here, that was isochronous real-time. The real-time part is a little detail, but the real-time part bypasses what we call the IP and TCP/IP protocol stack. It goes directly onto the Ethernet. The Ethernet, if you go back up, the Ethernet was what we called, let's see, where did we have the CSMA CD stuff? The Ethernet part here. That's also specified in norms and lower level communication. This is time consuming, so it goes directly onto the Ethernet and says, okay, we bypass this, so you get real-time data through this fast. And the isochronous requires this special component, RTech or AirTech 400 and 200, 2 ports and 4 ports on this one. Yes, and we are through to the programming model. Yeah, so this was a really quick introduction. We just looked at in the compendium and the figures, read through the compendium, and use the internet to look at information. We looked at the PLC Open homepage and then Profinet International, Profibus, Profinet International homepage, where you can find more information, because this is just an extract of what is a PLC and interfacing a PLC with sensors and actuators or equipment devices in the field or in the process, which you use to influence or make the process change, the state of the process change. Start a motor, restart a pump, or whatever. And then you get feedback in through a sensor that says, okay, the motor is starting, the pump is running, or the water is flowing, which is an analog input.